Okay, let's take a look at the properties of some amines. And it says here that the nitrogen atom in typical amines is sp3 hybridized. And there's no surprise there, right? We have 4 regions of electron density. We have a lone pair, 3 R groups. So sp3 hybridization. And the bond angles, it says here, are around 108 degrees, which is pretty close to what you would expect, the tetrahedral bond angle of 109.5 degrees. Now, the carbon-nitrogen bond length, and I know we don't discuss bond lengths a ton in this class, but it says here they're around 147 picometers, which is going to be a little bit shorter than carbon-carbon bonds and longer than carbon-oxygen bonds. And you want to remember that as we go across the period from boron to carbon to nitrogen to oxygen to fluorine, you want to remember that as we go from left to right, that the atoms actually get smaller. Okay, so oxygen is smaller and carbon is larger, and that's because of effective nuclear charge, and I'm not going to go into all that right now, but that's why the carbon-nitrogen bond is actually going to be longer than a carbon-oxygen bond, but it's going to be shorter than a carbon-carbon bond. Anyhow, it says here, under what circumstances would the nitrogen be sp2 hybridized? And the answer to that is going to be when the lone pair is participating in resonance, the nitrogen will not be sp3, but it would be sp2 hybridized. And one example that we saw in general chemistry, in organic chemistry 1 was an amide, and we're going to take a look at that in a little bit. Not right now, but in a little bit we'll take a look at an amide and we'll explain why that nitrogen is not sp3 hybridized, but it is rather sp2 hybridized. Now, when it comes to the chirality of an amine, you might take a look at an amine like this one and say, okay, well, my nitrogen has a lone pair, that's a group, and then it's got 1, 2, 3 different R groups on it, which is being illustrated here, R1, R2, R3, different colors. And you might think, okay, well, I've got 4 different groups, and so my nitrogen is chiral. And that is a good rationale, actually, to think that, okay, 4 different groups, therefore it might be chiral. However, it says here that amines are not chiral, or we say they are not optically active, meaning they don't rotate plane polarized light. And the reason why is because they invert so rapidly. So if we take a look on the next slide, you see here that the pyramidal conversion occurs very rapidly. So you see it says down here, we have a trigonal pyramidal and it's chiral, and over here it's trigonal pyramidal and it's chiral. But the barrier to inversion between these two is only 25 kilojoules per mole. And so the idea is that these two rapidly interconvert at room temperature. And so it essentially makes kind of like a racemic mixture in a way. And so the compound, or the nitrogen overall, is going to be achiral, right? It's not going to rotate plane polarized light, again, because this barrier to inversion is so low. So in case you've ever wondered that should answer it for you, that even if your nitrogen has 3 different R groups on it, the barrier to inversion is so low between the 2 trigonal pyramidal forms that it is not going to be chiral. So you don't even have to worry about that. Now, what about solubility of amines? If you think about something like ammonia, NH3, it's soluble in water. If you think about household cleaners like Windex, it has ammonia dissolved in it. And so we see a general rule here that if you have an amine that has less than 5 carbons, so if we have less than 5 carbons in our amine, it's generally going to be soluble in water. And so let's say you have something like 1, 2, 3, 4, let's say you have 1 butanamine. You'd say, okay, well, this compound has 4 carbons and 1 NH2 groups, and so it's going to be soluble in water, right? It's just kind of a rule of thumb that we can use here. Now, it says primary and secondary amines can intermolecularly hydrogen bond and have higher boiling points than tertiary amines. So let's unpack the 2 trends that are being illustrated on this slide here. And I'm going to start with these 3 compounds here, because here we have propane. Okay, we have propane here, then we have ethylamine here, and then we have ethanol here. Okay, so if we take a look at these 3 compounds, you notice that propane has by far the lowest boiling point at negative 42 degrees Celsius. And the reason why is because the only intermolecular forces that 2 molecules of propane would experience would be London dispersion forces. So we could put here London. Okay, London dispersion forces are the only intermolecular forces that would be experienced between two molecules of propane, and that's why propane is going to be a gas at room temperature, and it doesn't liquefy until below negative 42 degrees Celsius. Then if we compare these two compounds here, so if you take a look at the ethylamine and the ethanol, right, they're both capable of hydrogen bonding. We can see that the amine has two nitrogen-hydrogen bonds, and so that meets the requirement for hydrogen bonding. And then, of course, ethanol meets the requirement for hydrogen bonding as well. But why is it that ethanol has a boiling point that is so much higher than ethylamine? Well, the rationale is really nothing more than this. You guys know that oxygen is more electronegative than nitrogen, right? Oxygen has an electronegativity of about 3.5, whereas nitrogen has an electronegativity of around 3. And so, yes, there is a delta negative here and a delta positive here, and we could put a delta positive here. But when it comes to the oxygen-hydrogen bond, we have a stronger delta minus and a stronger delta plus. Why? Because the magnitude of the difference in electronegativity between the oxygen-hydrogen bond is going to be greater than that between the nitrogen-hydrogen bond. And so, yes, an amine can participate in hydrogen bonding, no argument on that, but it's not going to be as strong as that of an alcohol. And that's why we see such a marked difference in their boiling points. All right, now if we take a look at the trends of these three compounds on the bottom here, okay, so we have propylamine, ethylmethylamine, and we have trimethylamine. Well, all three of these compounds have the same molecular formula, and that molecular formula is C3H9N, but you notice a big difference in the boiling points of propylamine and ethylmethylamine versus trimethylamine, okay? And the reason why is because propylamine and ethylmethylamine are primary and secondary amines, and then trimethylamine is a tertiary amine. And you probably noticed the difference right away is that for the primary and secondary amines, we have nitrogen-hydrogen bonds, and so they can hydrogen bond amongst themselves, whereas in methylamine, there is no nitrogen-hydrogen bond. There's a nitrogen, it's got a lone pair, but there's no hydrogen attached to the nitrogen in a tertiary amine, and so it cannot hydrogen bond. So the strongest intermolecular force that two molecules of trimethylamine would experience would be dipole-dipole forces. And so it has a much lower boiling point than the propylamine and the ethylmethylamine, again, because it cannot hydrogen bond between intermolecularly between two molecules of itself, whereas propylamine and ethylmethylamine are both capable of hydrogen bonding. Another thing you might find interesting about amines is their odors, or maybe you find it uninteresting, but many small molar mass amines have unpleasant odors. And in case you're wondering, like, what does an amine smell like? Well, if you've ever smelled rotting fish, that's what amines smell like. So when fish decompose, it breaks down the proteins in them and releases amines, and a lot of them have that or produce that rotten fish smell. And there's two here, putrescine, which is 1,4-butane diamine, and cadaverine, which is 1,5-pentane diamine. And both of these compounds are found in rotting fish, and both of them are also found in urine and responsible for its odor as well. Now next we want to take a look at the basicity of an amine, okay? Because when you think of an amine, okay, one of the things that you should think of as an organic chemist is this, is that amines are organic, they are organic bases, okay? They're organic bases. They're not strong bases like sodium hydroxide or lithium hydroxides, but they are bases, okay? So it says here, amines are stronger bases than alcohols or ethers. Amines can be readily protonated by strong and weak acids. So here we have triethylamine, okay, and it's being reacted with acetic acid, right? This is just acetic acid here, and the pK of acetic acid is around 5. And you end up producing this triethylammonium ion here, which has a pKa of 10.76, and this is, of course, the conjugate acid of triethylamine. And then we have the acetate ion here. So if we labeled everything, this would be our base, this would be our acid, this would be our conjugate acid, and this would be our conjugate base. And you remember that when it comes to the equilibrium is always going to lie to the side of the weaker acid. So you remember that the lower the pKa, the stronger the acid. And so the triethylammonium ion has a pKa that's 6 orders of magnitude higher, and so the equilibrium is going to lie hard to this side, okay? And so what does that tell you? It tells you that triethylamine can very effectively deprotonate acetic acid. So it's a good idea to have a general idea of the pKa values of the protonated amines. Okay, so we started out with this one here. The triethylammonium ion has a pKa of around, it's 10.76, so we'll just say close to 11. And the reason why you want to have an idea of, how the basicity of an amine works, okay, when an amine is going to be a strong base or a weak base, is because many pharmaceuticals contain one or more amino functional groups and thus are sometimes marketed as salts. And you see some examples here. We have this propranolol compound here, which is used to treat hypertension, and it is administered as a hydrochloride salt. So you see the positive and negative charges there. Then we have Gleevec, which is a cancer treatment drug. And then you have Viagra as well, which is also administered as a salt. And so anybody who's dispensing medication should have a bit of an idea of basicity of amines, because their salts are so prevalent in marketed drugs. The table 22.1 shows us the pKa values of ammonium ions of several amines. And if we just take a quick peek at this here, you can probably notice some trends right away. If you look at methylamine, then you look at the methylammonium ion, we have a pK of around 10.6. Well, the triethylammonium ion had a pK of what? It was like 10.76. So you see they're in that 10.5, they're both in the same neighborhood. And in fact, if you look at all of these, if you look at the conjugate acid of methylamine, ethylamine, isopropylamine, cyclohexylamine, dimethylamine, diethylamine, trimethylamine, and triethylamine, look at them. They're all in the neighborhood of, I think the lowest one here is 9.8 and the highest one is around 11. So all of these have pKa's that are in the neighborhood, we'll just say between 10 and 11, okay? And I want you to keep that number in your mind, because we're going to look at aniline derivatives, and we're going to see that the conjugate acid of an aniline, which would be an aniline ion, is going to have a lower pKa, okay? So let's move ahead here. And it says here the pKa values of some other ammonium ions. So I just want to focus on the left-hand side of this table here, okay? So you notice that all of these ammonium ions here, these are all the conjugate acids of different anilines. So we have aniline, then we have, this is called the anilinium, so the anilinium ion, okay, which has a pKa of 4.6, then the N-methylanilinium ion, then the N,N-dimethylanilinium ion. So you can see that these, the aniliniums anyway, their pKa's are what? We'll just say around 5, okay? Close enough, okay? So you see that the pKa of these anilinium ions is around 5, whereas if we go back to this slide, the pKa of all the conjugate acids of these alkylamines was a lot higher. So what does that tell you, okay? Now remember, the stronger the acid, the weaker its conjugate base. So what that tells you is that an aniline is going to be a weaker base than, let's say, methyl or ethylamine. Now let's think about that. If we just sketch these up here and we say, okay, if we compare NH2 with an ethyl group, so this is ethylamine, and then we compare it to aniline. Okay, now why is it that the ethylamine is a much stronger base? Okay, so again, this is going to be stronger base, and therefore it produces a weaker conjugate acid. And this is going to be a weaker base, and therefore it produces a stronger conjugate acid. Now, why would that be? It's because of the lone pair, right? The more basic something is, the more available its lone pair is for protonation. So if we think about this lone pair, that lone pair is localized. It's just sitting there. This is localized. It is not going anywhere, so it is available to be protonated. Whereas the lone pair on aniline, I'm not going to draw all the resonance forms right now. They're drawn on a slide coming up. But we see that that lone pair is delocalized. Okay, so if it's delocalized, then it's not as available, right? It's delocalized throughout the entire molecule. and so it's not as available for protonation. So that explains why the aniline derivatives are going to be weaker bases, and hence when they get protonated, they produce stronger conjugate acids. So if you have to take some time to think about that, go ahead and do it, because make sure that you understand the difference between why an anilinamide is so much more acidic than an alkyl ammoniamide. Now, there's a couple other examples that he put in here in the table, and I think he just wants you to remember the concept of aromaticity, okay? So if you compare pyrrole and pyridine and their conjugate acids, you notice that the conjugate acid of pyrrole has a really low pK. I mean, this is borderline. I mean, this ion is borderline a strong acid. Now, why is this thing such a strong acid? Whereas when you have the protonated form of pyridine, and you would call this the pyridinium ion, why is this much more basic? Why is it not nearly as strong an acid? Well, the rationale is this, is that this lone pair, the one in pyridine, resides in an sp2 hybrid orbital, and this lone pair is not required for aromaticity. Okay, you don't need that lone pair for aromaticity, whereas this lone pair in pyrrole is required for aromaticity. Okay, and so when you protonate this and you make this form, you go from something that is aromatic to something that is non-aromatic, okay? So this compound is like, I don't want to be non-aromatic. I want to get rid of that proton, okay, so I can become aromatic, because this is going to be not as stable. Whereas when you protonate pyridine, you go from something that's aromatic, and the pyridinium ion is still aromatic, okay? So it's not going to be, the pyridinium ion won't be nearly as acidic. So make sure you remember your rules for aromaticity, and that you understand why pyrrole needs that lone pair to satisfy Huckel's rule. Now, in this slide here, it says that in general, if you have an amine with more than 5 carbons, those are only going to be slightly soluble in water. Okay, so what's the point? It says solubility of an amine can be enhanced by the presence of aqueous acid, because the protonated ammonium ions are cations and therefore water soluble. And so if you want to extract an amine from an organic impurity, it can be treated with acid, and therefore it gets converted into the ammonium ion. And remember, the ammonium ion is a salt, okay, and that is going to be water soluble. Let me give you an example. Let's say you had something like, I don't know, octylamine, 1, 2, 3, 4, 5, 6, 7, 8, okay? So let's say you have 1-octanamine or octylamine, whatever you want to call it, okay? This is going to be water insoluble, okay? If this is soluble in water, it's going to be very sparingly soluble in water. However, the compound would be soluble in organic solvents. And so the question is, how do you make it soluble in water? Well, you could treat it with an acid like HCl, and then you're going to end up with the hydrochloride salt. So if I just paste this over here, so we'll just delete this, okay? Then instead of having NH2, now we have NH3, and so we have a positive charge on our nitrogen, and we have the chloride like this, and so now we have the hydrochloride salt, and this is going to be water soluble. All right, there you go. And so you should know how to extract an amine from an organic impurity by converting it into a water-soluble salt. Now, this slide is nothing more than a rehash of some topics that I've already talked about in this video. It says here the pK of most alkyl amine conjugate acids was between 10 and 11, whereas the pK of the anilinum ions was more like 4.5 to 5, okay? And the rationale was why? Is that the lone pair on the nitrogen of an aniline is going to be delocalized, and you should all be able to draw these resonance forms that are shown here. And so if the lone pair is delocalized, it's less basic, and therefore it produces a more acidic conjugate acid. But to get into more details on different aniline derivatives, you see here that the basicity of the lone pair, or its availability, can be affected by having different types of or different types of substituents on the ring. And so here we have a methoxy group, and a methoxy group is actually an electron donating group. Now you might look at a methoxy group and say, well, I thought that oxygen was the second most electronegative element on the periodic table. Shouldn't it be pulling electron density away from the ring, like doing something like this? And yes, there is a dipole going in that direction. However, whenever you have a competition between induction and resonance, right? If you remember aereo, resonance wins out. And so this lone pair can be donated, okay? And I'm not going to draw all the resonance forms in here. And so you see that the lone pair, this lone pair in the paramethoxy aniline is going to be more basic. And so if it's a stronger base than aniline, it's going to produce a weaker acid. And we see that because we see a higher pKa, right? This is aniline right here. And then if we have a nitrile, okay, so here we have an electron withdrawing group, okay, this is pulling electron density away like crazy. And so this lone pair is going to be less available. And so if it's a weaker base, it's going to produce a stronger conjugate acid, and that's exactly what we see here. And so the conclusion is what's shown at the bottom. It says the presence of an electron withdrawing group like the nitrile group is also going to increase acidity, or as it says here on the slide, decrease basicity, renders the lone pair less available. Now there was a question that was asked earlier on in this video, and it said, when is a nitrogen going to be sp2 hybridized, okay? And if you take a look at this nitrogen here, you say, okay, well, it's got 3 bonds in one lone pair. Isn't it sp3 hybridized? But the answer is it is not sp3 hybridized, okay? This nitrogen that I have the arrow pointing to is sp2 hybridized. Now, why is that? It's because you can see that that lone pair is participating in resonance. And the only way that a lone pair can participate in resonance is if it is in a p orbital. So this lone pair is in a p orbital. Okay, that's why it can participate in resonance, right? If you look at this carbon, it's sp2 hybridized, so it has a p orbital on it. And this oxygen is sp2 hybridized, so it has a p orbital on it. So that means we have 1, 2, 3 p orbitals that are all overlapping, which allows that lone pair to be delocalized across those 3 atoms. And so when you see an amide, and you're going to see a lot of them moving forward in the class when we look at peptides and proteins, and you'll see a lot of them in biochemistry as well. And so you should be well aware that when you see a lone pair on the nitrogen of an amide, it is not basic because it is delocalized into the carbonyl group. And you see that shown in this electrostatic potential map where we have a big old delta negative up by that oxygen, which shows the delocalization of that lone pair. Now, staying in that biochemistry vein, okay, if you move into biochemistry, you're going to talk about physiological pH a lot, okay? So physiological pH is around 7.3. I know you could do some arguing about that. But anyhow, the bottom line, what you need to know for this class is that at physiological pH, the equilibrium is going to lie hard to the side of the protonated form of your amine. So amines exist primarily as ammonium ions. And I'm not going to ask you to use the Henderson-Hasselbalch equation that you used in general chemistry 2, but you can use the Henderson-Hasselbalch equation to calculate the ratio of the protonated form versus the free base form. Again, I won't ask you to do those calculations, but they can be done using the Henderson-Hasselbalch equation. Okay, first question says, rank this group of compounds in order of increasing boiling point. You can see that all these compounds are isomers. They're all isomers of C6H13N. And if you take a look, you can see this one is a tertiary amine, this one is a primary amine, this one is a secondary amine. So the tertiary amine is definitely going to have the lowest boiling point. So we'll put lowest boiling point here. And then between the primary and secondary amine, well, the primary amine has 2 nitrogen-hydrogen bonds, whereas the secondary only has 1. And so the primary amine is going to have more hydrogen bonding, and so it's going to have the highest boiling point. All right, next question, 22.5. Says to identify whether each of the following compounds is expected to be water soluble. Well, if you remember, our rule was If we had 5 carbons or less with every nitrogen, it's going to be water soluble. And you can see that in the first compound, we have an NH2 group, which would help to render the compound water soluble, but it has a total of 8 carbons. And so we're going to say, no, this compound will not be water soluble since it has 8 carbons per NH2. Okay. And the second one, this is isopropylamine. This is a yes for sure since it has 3 carbons per NH2. And the last one has 6 carbons, so you might say no, but but it breaks down to being 3 carbons for each NH2 group, right? Because we have 2 NH2 groups and 6 carbons. So we'll say yes since 3 carbons per NH2 group. Okay, so the second 2 compounds will be water soluble, first one not water soluble. Next question asks identify which compound is a stronger base. And so remember, the stronger base is the one where the lone pair will be most available. Okay, available. Another way of saying that is saying the lone pair will not be participating in resonance. So if we take a look at the first one, if I put a blue lone pair here and a red lone pair here, well, you can see the red lone pair is less available. Why? Because it can participate in resonance. Okay, I'm not going to draw the contributor here, but the blue pair is localized. Okay, and then you could say the red pair is delocalized. And so the first one, the one with the blue lone pair, this is going to be the stronger base. Okay, and if you want to write that in, you could put localized. And for the red one, you could put an arrow and say delocalized. Okay, that's the idea here. All right, let's take a look at the next one. The next one demands that you borrow some of your information from the chapter on aromaticity. And so if we look at the first one, this is pyrrole. This lone pair that I just put in red, that lone pair is required for the compound to be aromatic. But if I put a lone pair on this one in blue, okay, now if this lone pair, pay close attention, if this was in a p orbital, then we would have a continuously overlapping system of p orbitals because every one of these carbons is sp2 hybridized. So we meet the first criteria for being an aromatic compound, but you would have a total of what? 1, 2, 3, 4, 5, 6, 7, 8 electrons in that ring. And so that is not a Huckel number, right? 8 is not a Huckel number. 4n plus 2 is not satisfied ever to give you 8. If n is equal to 0, you get 2. If n is equal to 1, you get 6. And if n is equal to 2, you get 10. So 8 is not a Huckel number. And so what does that tell you? It tells you that that lone pair is not participating in resonance. So let's erase that p orbital. And we'll put here, doesn't satisfy Huckel's rule, not involved in resonance. Another way you could say it is it's not delocalized. Whereas this pair is delocalized. And so the compound on the right is going to be the stronger base. Okay, so if you have to go back and review Huckel's rule, make sure you do that. The next one should be a little less complex than that last one. So if I put a green lone pair on here, and let's say I put a blue lone pair here, well, you can see the blue lone pair is delocalized. You should all be able to draw this resonance form with relative ease, whereas the green lone pair is localized, and so this is going to be the stronger base here. And you have to go back to your aromaticity rules for the last one. Okay, if we put the lone pair here, this lone pair is required for aromaticity, and so we would say that this lone pair is delocalized, whereas the blue lone pair is not required for aromaticity. So these are localized, and so this compound is going to be the stronger base. Okay, and the last question is rank the following compounds in terms of increasing basicity. So if we put a lone pair, I'll put a blue one here, we'll put a black one here, and we'll put a red one here. Okay, so if we compare this compound and this compound to the compound that I don't have a circle on, okay? Well, what you notice is that a bromine is an electron withdrawing group, okay? And the carbonyl is electron withdrawing as well, whereas an alkyl group like a methyl group is an electron donating group, okay? These are electron donating groups. Now, all of these lone pairs, the blue, the black, the red, they're all delocalized, but which one is going to be the most available? Well, the one that has the electron donating groups is going to be pushing electron density this way. And so this one is going to be the most basic, okay? And the one with the electron withdrawing groups is going to be pulling electron density away from the nitrogen. So that lone pair, the black one, is going to be the least available. So this will be the least basic, and the other compound with no substituents on it is going to be somewhere in between.